So now we're going to look at entropy. So what is entropy? So entropy is is a measure of the disorder of a system. How are the particles arranged? Are they arranged in order or are they arranged in a disorder manner? For example, a gas will have the particles moving at random from one place to another. So we will say that the gas has more disorder or more entropy than a solid. A solid has particles that are arranged in an orderly manner. Okay. But a gas, the particles move at random. They move in a very haphazard manner. So in science, we will say that the gas has more entropy than the solid. Whenever energy freely transforms from one form to another, the direction of transformation is towards a state of greater disorder and therefore towards one of greater entropy. The greater the disorder, okay, the higher the entropy. That is why I say the gas has a higher entropy than a solid. All right. So if you remember the second law of thermodynamics, we were saying that natural system tends to disperse from concentrated and organized energy state towards diffuse and disorganized energy state. Energy tends to degrade and disperse with time. So the total amount of entropy in any system tends to increase with time. So check this out. Your garage gets messier every week. In this case, the entropy of your garage is obviously increasing. Okay? We're talking about the increase in disorder. That's how you need to think about entropy. You arrange your room in the morning, you make sure you tidy everything, you fix your bed. And as the day goes by, you will realize that your room gets messier. All right? You sit on your bed, the activities of the days tends to make your room messier. So by the end of the day, you realize that the order that you had in the morning has greatly reduced. So the disorder has increased. So that's how you need to think about entropy, the degree of disorder of a system. In this case, your room is a system. Now let's talk the next term here, specific heat. We've talked about this already. It is the temperature needed, or is a heat. I mean, it's not the temperature, sorry. Is a heat, is the amount of heat required to change the temperature of a 1 unit mass of a substance by 1 degree Celsius. So if you put 1 kilogram of water or 1 gram of water on a stove, the amount of heat energy that amount of water will absorb to change temperature by 1 degree Celsius, let's say it moves from 20 to 21, that amount of heat is what we call the specific heat capacity. Okay. So the thermal inertia that indicates the resistance of a substance to change temperature. So some substances have very high specific heat, like water. Water would absorb a lot of heat energy for its temperature to change compared to a metal like aluminum. To heat up aluminum is much easier than to heat up water. Substances have their own specific heat capacity. Okay. Filling in a hot apple pie has a greater specific heat capacity than the crust. Watery filling has more specific heat capacity for storing heat than pie crust. Okay. The high specific heat capacity of water. Okay. I said water is an example of a substance with a very high specific heat. Okay, it has higher capacity for storing energy than almost any other substance. It involves various ways that energy can be absorbed. Increase in jingling motion of molecules, which raises the temperature. Increase in the amount of internal vibration or rotational within the molecules, which becomes potential energy and doesn't raise temperature. Then the water molecule can absorb energy without increasing translational energy. Specific heat affects climate. Okay. For Europeans, in addition to warm jet streams in the atmosphere, the current in the Atlantic Ocean carries warm water northeast from the Caribbean region and retains much of its internal energy long enough to reach North Atlantic Ocean. The energy release is carried by westerly winds over the European continent, which has a higher specific heat. Water or land? Obviously, water. Okay. Water has a higher specific heat. It takes much more heat to heat up water than to heat up land. That's how you need to think about it. So let's look at thermal expansion. What is expansion? Due to rise in temperature of a substance, molecules jiggle faster, move further apart. Most substances expand when heated and contract when cold. So expansion is increase in volume, contraction is a reduction in volume. Look at the railroad tracks closely laid on winter days expand and buckle in hot summer. Warming metal lids on glass jar under hot water. It loosens the lid by greater expansion of the lid than the jar. So all this demonstrate that objects expand when heated. So the extreme heat of a summer day causes the buckling of this railroad track. Okay. Look at the railroad track when it's too hot, it buckles up. This gap in the railroad of a bridge is called an expansion joint. It allows the bridge to expand and contract. When stringing telephone lines between poles in the summer, it is advisable to allow the lines to sag. Telephone lines are longer in a warm summer and shorter in a cold winter. Hence, they sag more on hot summer days than in winter. If the lines are not strong with enough sag in summer, they might contract too much and snap during the winter, especially when carrying ice. When an earth hits a metal ring that has the same inner diameter as the diameter of the metal ball. When the ring is hot, the room temperature ball fits into the hole with more room to spare. The ring is heated, all parts expand. This means expansion of the inner and outer circumference, inner and outer diameter, width, you name it. The whole expands just as if it were a solid metal. How about that? Let's look at metal expansion. The bimetallic strip, brass and iron welder together. When the strip is heated, the brass expands more than the iron. When cold, the brass contracts more than the iron. Due to this behavior, the strips bends as shown. You look at it. This bimetallic strip is what is used in the iron that we use in heating up our clothes. Okay. So when it heats up, you see at one point the brass is going to expand. It causes the iron to go off. Okay. And when it cools, it joins back, establish the connection, and electricity starts flowing again in your iron. That's why it comes back on. So the another application is a thermostat. Okay. When a bimetallic coil expands, the ball of the liquid mercury rolls away from the electric contact and breaks the electrical circuit. When the coil contracts, the circuit is complete and all of that. So now let's look at the expansion of water. Water is a very weird substance. So remember, all other substances, what happens is when they're heated, they expand, and when they are cold, they contract. But that is the opposite for water. Ice has a larger volume than liquid water. That's weird. Because water expands when it turns into ice. So water is the only substance that is going to actually contract when you heat it. So what explains it is that ice has an open structure crystal resulting from strong bonds at certain angles that increase its volume. This makes ice less dense than water. Okay. So remember, water is an exception. Water is going to contract when you heat it up, but it expands in the form of when you cool. Okay. So between 0 degrees Celsius and 4 degrees Celsius, water does not expand with temperature. Okay. As temperature of 0 degrees water rises, contraction occurs due to melting of ice in water. Contraction of water continues until 4 degrees Celsius. Water at 4 degrees Celsius. Water has the smallest volume and the greatest density at 4 degrees Celsius. By the time water reaches 0 degrees Celsius, water freezes to become ice and it has the largest volume and the lowest density. Water has the largest volume at 4 degrees Celsius, at 0 degrees Celsius, and the lowest density. That's why you see ice floats on water. It floats on liquid water because ice has a lower density than liquid water. And so this is a graph that explains that. Okay. We're not going to go into that detail. When a sample of water is heated, what happens? It first contracts. So when you heat water, it first contracts. It will not expand. It's the opposite. Okay. When a sample of a 4 degree water is cool, when you cool it, what happens? It expands. So it's the opposite. So if you take a sample of a 4 degrees Celsius water, and you try to cool it, it will expand because it's turning into ice. And remember, ice has the largest volume and the lowest density. So now let's look at this. This has actually a very nice application because as water cools in winter, it becomes more dense and sinks. Okay. The sinking continues until the entire pond is at 4 degrees Celsius. Then, as water at the surface is cooled further, it floats on top and freezes. Okay. Once the ice is formed, the temperature lower than 4 degrees Celsius can extend down into the pond. So because of this, you see what the aquatic life, like the fish, the plants, they are able to survive underwater because When water freezes, the temperature drops, the volume increases, and it floats. So it allows the freeze water to remain at the surface. Because if water had to freeze and sink, it is going to kill all the fish and all the aquatic life. So because of that property of water, it's actually nice because it allows the aquatic life to survive. Now let's look at water and the ice application I just explained. Cooling of water in winter becomes more dense and sinks, continuous sinking until the entire pond is 4 degrees Celsius. Further cooling of water at the surface, the water floats on top and can freeze. The ice formation. Lower temperature lower than 4 degrees Celsius can extend down into the pond. Okay. So because of that, we are able to have during winter we are able to still have the fish underwater survive because the ice is going to remain at the surface. Okay. All right. I hope you enjoyed it. Make sure you take down your notes.